Morning to one and all. I am Parthiban, working as an assistant professor in the Department of Electronics and Communication. Now I am going to talk about the subject called satellite communication, which is coming under the regulation R 2021. The subject code is CEC 352. Now I am going to talk about the topics, that is the satellite orbits and its uses. In the last session, we have talked about the various satellite orbits, that is LEO, MEO, as well as both GEO. So the LEO is generally positioned around 500 to 2000 kilometers altitude. It exhibits a much shorter period, that is up to 95 to 120 minutes only. The LEO satellites provide a very high quality communication, but the biggest problem of LEO is the need of many satellites to provide a global coverage. In the next three, we are going to see about the MEO. So MEO is nothing but the medium Earth orbits. Actually, it is greater than LEO, but it is lesser than GEO. Generally, we need a dozen satellites to provide a coverage, that is global coverage. So that is what the MEO problem lies is. MEO can have a larger populations requiring fewer hardwares. The disadvantages mainly lies in the delay. That is around 70 to 80 milliseconds of delay. That is quite possible in MEO. To overcome all these things, we are going to use the GEO. So GEO provides the global satellite communication, which is around 36,000 kilometers away from the Earth. The rotation resembles as if like our Earth. That is why it is called a geostationary Earth. So it has the same 24 hours period. It almost resembles as if like our Earth rotation. So we need a minimum four geo satellites to provide a global coverage. Next, this is the diagram that depicts the satellite rotation around the Earth. So it clearly states a geosatellite's position, which is governed and monitored by Earth, which is as seen from the moon. Then we are going to talk about the various governing parameters which are very vital in satellite communication. So these parameters are virtually nothing but the orbital parameters that we can say. So these are the prime factors that helps to position the satellite as well as the maintain the satellite. First, in the classification of orbital parameters, the first and foremost one is called the sub-satellite path, which is nothing but the path that is traced out on the Earth's surface directly below the satellite. We can say it is nothing but the trace drawn from the Earth's surface, that is called SSP, which is also called sub-satellite path. Then the next one is apogee. Apogee is nothing but the maximum distance between the satellite and the Earth, that is called apogee. Perigee is the opposite one, which is nothing but the closest distance between the Earth to satellite is called perigee. The apogee and perigee plays a very crucial role in satellite communication. Then the important other parameter is the fourth one, which is nothing but the line of absence, which is nothing but the line that is drawn between the apogee and perigee via the center of Earth. These all the prime factors that needs to be taken into consideration before launching the satellite communication. The next one is ascending node. It is nothing but the point where the orbit crosses the equatorial plane going from south to north. The opposite is one is called a descending node, which is moves in the opposite direction, which is the point where the orbit crosses the equatorial plane going from north to south. The only difference between ascending and descending lies in the south to north, north to south only. Then the next important parameter is called the line of nodes, which is nothing but the line joining the ascending and descending nodes via the center of the Earth, which is also an important parameter in deciding the position of the satellite, the line of nodes. The next one is the inclination. The inclination is very important with respect to the satellite as well as the Earth position. It is nothing but the angle between the orbital plane and Earth's equatorial plane. It is measured from the ascending node, from the equatorial orbit to the orbit that is governing the satellite, which is going from east to north direction. The inclination angle decides the connectivity as well as the reception capability of both satellite as well as Earth station. The antenna should be positioned in a perfect inclination. Even a 1 degree of tilt can change communication receiving capabilities. Then the next important parameter is a declination, which is nothing but the angle between the equatorial and the line drawn between the centers of the Earth and the Sun. The angle of tilt is also called as declination. The angle of tilt is very much important in respective communication passage is concerned. The next one is called prograde orbit, which is nothing but the orbit that moves in the satellite as if like the same Earth rotation. It resembles the same as if like a rotation. That is from west to east. That is called west to east is called prograde. So prograde orbit is nothing but it's also called a direct orbit. The opposite one that is called retrograde orbit that will move in the opposite direction as if like Earth's moving, which is east to west, not like the west to east. So the opposite is called a retrograde orbit. Then the argument of perigee, which is nothing but the angle from the ascending node to perigee that is measured in the orbital plane at the center of the Earth. Indicates the direction of satellite motion. So argument of perigee is an important parameter that gives the direction of satellite motion. Then the important parameter is right ascension of ascending node, which is nothing but the angle measured in the eastward from the equatorial plane to the line of absence. Then a mean anomaly is the average value of the angular position of satellite with reference to the perigee. So this parameter indicates the different in position from the natural. Then coming on to the next one that is called true anomaly, which is nothing but the angle from perigee to satellite position that is measured at Earth's center. So these are the vital important parameters that decide the position of the satellite. Whether if there is any deviation occurs, that should be controlled from the Earth station by sending the pulse through the jets. So even a 0.1 degree tilt can change the communication characteristics of a satellite. The 0.1 tilt not only in the Earth antenna but also in the satellite antenna also. So both antennas should be kept intact without any deviation for not even a 0.1. Even a 0.1 degree tilt in per year that will accumulate and it will make a huge difference in the communication satellite. The diagram that depicts the inclination, the what is apogee, what is perigee, what is right ascension of nodes, which one is the equatorial plane, which one is the inclined plane, which one is the polarized plane. So the diagram clearly depicts in what way the rotation of satellite can be, whether it can be revolving around the equatorial plane, whether it can be inclined rotation, or whether it can be based on the polar rotation. So based on these three types of directions, we can have three possible satellite rotation as well as satellite communication properties. We can have a polar satellites, we can have inclined satellites, we can have equatorial orbit oriented satellites. Then coming on to the other important parameters that is called orbital elements. The orbital elements are also very important as if like orbital parameters. Some of the parameters are both common in many ways. For example, the orbital elements in the first one is called a semi-major axis, which is nothing but the major axis of an ellipse, which is the radius is called small a, that is called semi-major axis. In the elliptical structure, the eccentricity is very important, which is nothing but the ratio of major axis to minor axis that is called eccentricity. So E is an important parameter. Based on the E, the shape of the ellipse can be proved. Then coming on to the next one, that is mean anomaly, which shows the difference between the original value and the deviated value. From the mean anomaly, we can analyze the deviation or difference. Then coming on to the next one, that is augment of perigee. It shows the position of the satellite, how far it has been deviated from the Earth. That can be known from the argument of perigee. Then inclination angle for both satellite as well as for Earth station is very important. See, the inclination only provides a very good coverage. Then the right ascension of ascending nodes gives the satellite a rotational position. So these are the vital parameters that can be taken into account. Then coming on to the semi-major axis, from the diagram we can see the major axis is nothing but the which covers from F1 to F2 and it is a center. So the one half portion is called the semi-major axis. The next one is called the semi-minor axis, which is nothing but the axis that is in the vertical position. Major axis is nothing but in the horizontal position. So major axis is represented as small a, minor axis is represented as small b. The eccentricity is represented as small e. So which decides the shape of the satellite orbit. So this barometer indicates the deviation of orbital shape from a perfect orbital position. So what is E? E is nothing but the eccentricity. E is equal to root of A square minus B square divided by A, where A is nothing but the semi-major axis, B is nothing but the semi-minor axis, as well as we can say the eccentricity is 0, then naturally it is not an elliptical orbit. If eccentricity is 0, then it will be a circular orbit only. So under the case, the both A and B are equal, we can say it is a circular orbit, it is not a elliptical orbit. So the value of eccentricity will always be greater than 0, but it should be less than 1. So for various positions of eccentricity, we can see the diagram. When E is equal to 0, we can see a perfect circular shape. When E is equal to 0.5, it may be somewhat a semi-elliptical. If E is equal to 0.75, it was more or less elliptical section. When E is equal to 0.9, you can see a perfect elliptical structure. So based on the value of eccentricity E, which directly depends on the semi-major axis as well as semi-minor axis, we can see the difference when E is equal to 0, when E is equal to 0.5, when E equal to 0.75, and when E is equal to 0.9. So under the case of 0.9, you can have a perfect elliptical system. Rather than we can say a more elliptical nature of orbit position, that is lies factors that we have discussed. Generally, the atmospheric drag, which is also a common phenomena, but this won't affect the geo satellite, but other satellites are get affected because of the atmospheric drag. Because the atmospheric drag is very much pronounced in the range of 1,000 kilometers. Particularly, the less than 1,000 kilometers satellite are severely affected by the atmospheric drag. Our Earth is not a perfect sphere. We can say technically it's a sphere, but in the true way, we can say our Earth is a oblate spheroid. It is not a perfect sphere. So the effect of non-spherical Earth also should be taken into consideration before deciding on the other Earth. For a spherical Earth, we can expect a uniform mass and we can have the Kepler's third law in motion. That is, n naught is equal to root of mu by a cube. So the n naught indicates when the Earth is of a perfect spherical Earth. But in practice, our Earth is not a perfect spherical Earth. So the orbital perturbation should be taken into account in both ways, whether we can considering the Earth as a perfect sphere, whether we can considering our Earth as an oblate spheroid. If we are taking our Earth as an oblate spheroid, we have to apply the formula that is n is equal to n naught into 1 plus k1 into 1 minus pi 1.5 sine square I divided by a square into 1 minus e square to the power of 1.5. So n should be considered for oblate spheroid. N naught should be considered for a perfect sphere. K1 is nothing but a constant, which is given by 60,063 kilometers. The Earth oblateness has negligible effect on A if it is known. The mean motion is easily calculated. The orbital period can be easily calculated by means of anomalistic period. So the anomalistic period P is equal to nothing but 2 pi by n. So which gives the perigee to perigee distance, or we can say period. The station keeping. So what is station keeping is, in spite of all the problems that are facing that makes the satellite to drift or deviate from its original position, we have to maintain the constant orbital position. That is called station keeping. The station keeping maneuvers can be done by means of the earth station. So there are two types of maneuvering can be done, in the east-west direction, the other one in the north-south direction. So both should be done. The satellites generally in the 6/4 gigahertz band must be kept within 0.1 degree of destinational latitude position, longitude position. And in the 14/12 gigahertz band, it should be kept within plus or minus 0.05 position of the designated longitude as well as latitude positions. So these maneuvers should be kept intact. So we have to address all the ill effects of moon's gravity, sun's gravity, earth's gravity. So despite this, we have to maintain the satellite orbit intact without any deviation. So we have to compensate for all the deviations. This is what the station keeping will be doing. Generally, the rate of inclination per year is around 0.85 degrees per year. This is the normal case of a study that can be taken into account. So this deviation is occurring due to the sun, moon as well as earth. So to prevent the shift in the inclination, we have to extremely maintain the control by means of sending the pulse from the earth station, that is jets that can be induced to produce pulse, compensate for the losses that are occurring. So these are the various references that I have made. So with that, I am winding up my lecture, thanking you one and all for hearing the lecture.